Hey there, and welcome. Today, we're going to jump into a really core concept in mathematics, solving systems of linear equations. Now, that sounds fancy, but all it really means is we're on a mission to find the one single exact point where two different lines cross each other. I mean, think about it like this, right? You've got two straight roads stretching out across a map. As long as they're not perfectly parallel, you know they have to intersect somewhere. Our job today is to become master map makers and find the precise coordinates of that intersection. And that is really the hurt of the problem. A single linear equation, something like y equals 2x plus 3, well, it has an infinite number of solutions. It's an entire line of points. So to pin down just one specific point, we need a second equation, a second line, to see where it crosses the first one. So here's our game plan for today. First, we're going to quickly cover why one line just won't cut it. Then I'll introduce you to your two best tools for the job: substitution and elimination. After that, we'll walk through some examples step by step, tackle a couple of tricky cases, and finally, we'll talk about why this actually matters in the real world. Okay, first things first, let's make sure we're all on the same page and define what it is we're actually trying to solve here. So a system of linear equations is just a group of two or more lines that we're looking at all at once. And the solution we're hunting for? It's that one special ordered pair, that one single x comma y point that exists on both lines at the same time. It has to work for every single equation you've got. All right, so how do we actually find that point? Well, we have two main methods in our toolkit. You can think of them as two different keys to unlock the very same puzzle. And the trick is just picking the right tool for the job. Substitution is your go-to method when one equation basically just tells you what a variable is, like y equals 2x minus 1. It's already solved for you. On the other hand, elimination is perfect when you see that the variables are all lined up nicely and you can just add or subtract the equations to make one of the variables, well, disappear. Substitution is kind of like a four-step dance. First, you get one variable all by itself in one of the equations. Second, you take what that variable equals and you plug it into the other equation. That's the big move. It leaves you with just one equation and one variable. Third, you solve that much simpler equation. And finally, you take that answer and plug it back in to find its partner. The elimination method has a similar flow. First, you might have to tweak the equations a bit so that one of the variables has perfectly opposite numbers in front of it, like a positive 3y and a negative 3y. Step 2 is where the magic happens. You add the two equations together, and poof, that variable is just gone. After that, it's just like before. Solve for the variable that's left, and then plug that number back in to find the one you eliminated. All right, that's enough theory. Let's get our hands dirty and actually see these methods in action. This is where it all starts to really make sense. Okay, check out this system. The first equation is practically screaming at us: use substitution. See how the y is already all by itself? The equation is literally telling us that y is the exact same thing as 2x minus 1. So we do what it says. We take that 2x minus 1 and we substitute it in for the y in the second equation. And just look at that. We're left with one simple equation that only has x in it. Problem solved. Well, almost. And from here on out, it's just some straightforward algebra. Combine the x terms to get 3x, add 1 to both sides, which gives us 6, then divide by 3. And there you have it, x equals 2. We're halfway home. Now we just got to find y. We can take our answer, x equals 2, and plug it back into either of the original equations. But let's be smart about it. That first one is way easier. So y equals 2 times 2, which is 4, minus 1, gives us 3.
And boom, there it is, our solution. The one and only point where these two lines cross is at 2, 3. That's the single coordinate that makes both of our original equations true.
Okay, on to the next one. This system is just perfectly set up for elimination. Can you see why? Take a look at the y terms. We've got a plus 3y in the top equation and a minus 3y in the bottom one. They're practically begging to be canceled out. And that's the real beauty of the elimination method. We can just add these two equations together straight down. 2x plus 4x gives us 6x. The positive 3y and negative 3y, they cancel out to 0. Eliminated. And on the other side, 12 plus 6 is 18. And just like that, we have a super simple equation, 6x equals 18. Solving 6x equals 18 is easy, right? Just divide both sides by 6, and we get x equals 3. Now, same as before, we need to find y. we'll plug x equals 3 back into one of the originals. Let's use the top one. So 2 times 3 is 6. The equation is now 6 plus 3y equals 12. Subtract 6 from both sides, you get 3y equals 6. Divide by 3, and you found that y equals 2. And there we go. The meeting point for this system is the ordered pair 3, 2. By just lining them up and knocking out a variable, we found our answer. Now, it's not always going to be so clean and simple. Sometimes, when you're looking for that single intersection point, the math gives you a really weird result. Let's take a look at what that means. So you might run into two strange situations. On the left, you've got no solution. Graphically, this just means your lines are parallel. They have the same slope, so they run side by side forever and ever, but never, ever cross. When you try to solve this with algebra, you'll end up with something totally nonsensical, like 1 equals 3. That's a huge red flag from the math telling you, hey, there's no solution here. Then on the right, you have the exact opposite, infinite solutions. This happens when your two equations are actually the same line, just in disguise. Algebraically, all your variables cancel out, and you're left with a statement that's just true, like 2 equals 2. That means any point on the line is a solution. So, why are we doing all this? Is it just for fun? Well, yeah, but it's also because this isn't just some abstract math puzzle. It's an incredibly powerful way to model and solve all kinds of problems you'll find out in the real world. But before we get there, let's talk about avoiding some common mistakes. First, always double check your signs, especially when you're multiplying. One little negative sign can throw the whole thing off. Second, remember you're looking for a point, which has two parts. Don't find x and then forget to go back and find y. And finally, the best way to know you got it right, plug your final x, y point back into both of the original equations. If they both work out, you can be 100% confident in your answer. Okay, so let's talk about a huge real-world application, business. Every company on the planet wants to know its break-even point. That's the magic number where the money they're making, their revenue, is exactly equal to the money they're spending, their cost. It's that perfect balance of zero profit, zero loss. And guess how they find it? With a system of equations, of course. Imagine your cost to make X products is a flat $500 plus $10 for each one. And your revenue is $25 for each one you sell. You've got two lines. To find where they cross, your break-even point, you just set them equal to each other. In a case like this, you'd find you need to sell about 34 of them just to break even.
So we've gotten pretty good at finding where two straight lines meet. But that brings up an interesting question, doesn't it? What happens when the paths aren't straight anymore? What kind of math would you need to find the exact points where, say, a line crosses a circle, or where two circles overlap? Well, that's exactly where this journey leads us next.